So in the last lecture where we up to which point we have discussed, I think these different types of delays, and then this uh, exercise I gave for calculating the delay between the A and B, the data transferred by A to B. Okay, so in a real internet, we can also see that delay. Let us say, for example, if you want to know that, okay, from a certain place, what is the delay? Suppose you access from my place to suppose that Google, right? So how what is the delay between let's say bits PILANI and the Google? So uh, so how to do that? There is an application which is called as a traceroute application. So if you go to the traceroute.org, so you can also check it. I will show you the demonstration as well. So that you can also do at your side. So first I tell you that how it works basically, this traceroute application. Also this exercise is included in your first lab also. So there also you will do. So I will not explain much in more detail, but give brief idea that how this application is calculating the delay between the two locations, right? So uh, so what it does, say for example, here you can see this is a and this is a B. So let us say this is so if at A I want to find the means latency between A to B. So there may be a multiple hops are there or nodes are there between A and B. So this, if I run the trace route from A to B, then this trace route program will send uh, 3 packets at a time, and 3 packets it will send, and these packets will be returned by the router. Usually router don't return the packet actually, because router is not ultimate destination. Router cannot be ultimate destination, right? But in this application, what happens, this a protocol use which is name is ICMP. We will learn about this protocol later in our course. Just here I tell you that ICMP stand for Internet Control Management Protocol, right? So it is Internet Control Management Protocol. Management protocol. So as the name of the protocol suggests that, okay, find some control management related operations we can do. So this ICMP enables that router needs to send a reply back to the this sender, and with the help of this reply, the A can calculate the latency between itself and this router, let us say R1, right? So then it will find the latency of this. So why 3 probes it is sending? 3, because there may be possible that 1 or 2 packets might be dropped. So at least one will reach, and then I will get the delay estimate between the delay measurement between the A and R1. So that is simple. So at the time when it is sending the packet, so it note the time as T1. When it receive the this reply from the router, then the time T2. So T2 minus T1 is a basically delay, right? So this is now then it will send again 3 packets, and that these packets will be reply back by the second router on the path between A and B. Okay, so then it will come to know the latency between let us say this is R2, so A and R2. So like this, it sends the packet until the packet is not reached to the this destination, right? So the to which the packet is not reached to the router that is connected to the destination, right? So it will get the delay measurements for all the hops between A and B, right? So this is the functionality. Now how actually it is achieved, okay, that is something is hidden in this protocol. So right now I don't want to talk about this protocol. So I want to show just a simple demonstration. So let me share my other screen so you will be able to see. Yeah. So, okay. So, are you able to see the current? You can say my desktop. Are you able to see what?
Yes, sir.
Yeah. So here you can see. So there is a when we will type traceroute.org, traceroute.org. So then this site will be opening. Here the different country name is given. You can choose any country. Yeah, some of the traceroute means some of the countries ISP's traceroute is not working. That you will find, but which I have chosen the traceroute from. Uh, if you select the India, then you will get three these autonomous systems. Basically, these service providers have been given unique ID for their network, which is called as a autonomous system number. So this is AS number. So three AS numbers which provides this trace route service. But all three are not working for me, at least at my side. So I'm not using right now. I'm using the trace route from Australia. So and within, so if you click the country and then from Australia, I choose that Telstra. That's it. You can choose any one of them, and then this page will be open. Here in this page, you have to say that okay, what test you want to perform. So we want to perform IPv4 trace, right? Uh, then there is IPv6 also is there protocol, you know that. So, but yeah, we'll right now we'll just look at IPv4 trace. Then the which router location. So suppose I want to find out that okay, that Washington DC router is there. From this router to bits Pilani, what is the route actually, and then what is the latency total. So if so here I will specify the host name. So www.bits-pilani.ac.in, and then I'll say go. So then it will show this kind of output. So basically, it says that www.bitspilani.ac.in, the IP address of the Bits Pilani is showing here, and it shows the trace route of maximum 30 hops, because that's the idea that in internet between any two endpoints there will be no more than 30 hops. 30 is also more. Basically, it's within the 15 hops you can reach between any two endpoints. So then it sent these 60 byte packets, ICMP packets, and the important thing that we need to observe is that we can see these the latencies which are showing. So this is with respect. This is the first hop between from the Washington DC to DC router to this Bits Pilani route. So this is a first router, and this is the name of their router and this IP address, and these are the three packets latencies there, right? So 2 is shown here, third also. So okay, maybe 2 might have only replied, so it is showing only 2. Then this is, so you can see this is for the second hop, then third hop, then fourth hop, fifth hop, like that. So till ninth hop it is showing, and still it is not reached to the bits Pilani exit, right? So after, so it is not necessary that okay, you may always get the path from everywhere, because it also depends somewhere this ICMP protocol that is blocked. So means that's why you are getting these stars. So in the subsequent hops, it is not getting any response from these places. So that ICMP protocol is not allowed in these networks. So that's why you are getting no response. No response means star. Similarly, I will want to show that another thing. So say Washington DC to, if you go say google.com, so it is reaching up to the Google. You can say this is one of the you can say Google server. You know, Google don't have just one server, multiple servers are there. So DC to the nearest server is the 14 hops away, right? So which is currently for which the trace route is calculated. So, and you can see this 6.704 millisecond is the latency. And the first hop is this one, you can say 0.8 millisecond. Second hop, it says 0.823. So 2 samples it got out of 3 probes. Similarly, then here it is 6.336, and then 6.134 fifth hop, then 6.947, and so on. So this trace route means gives you the latency between any two hops. Okay, so now we will okay, So I think slides are visible to you. So this is about the delay. Okay, so now why we have emphasized on the delay much? So because when we calculate the performance of the, when we want to, I want to measure the performance of the network. So network performance parameters, one of the parameter is the delay. How much delay is there? So that's a one you can say parameter. And because if the between source and the destination A and B, how much time it is taking that packets are delivered from A to B. So that is a one concern for an application, that okay, how much delay is there. So some applications are delay sensitive, real time application. The packet should reach within some threshold time. If it is not reaching, then it is as good as considered as it's not reached, right, within that time frame. So the delay is a one parameter. Packet loss can be another parameter. For some application, say for example, for some application, packet loss is not a major concern. Packet maybe one or two packet can be lost, means over after 100 packets transfer, like streaming applications. If in between one or two packets are lost, but the delay is something critical for that. The packet should not be delayed much, but losses can happen. Like we are talking over a phone, if one or two words maybe not no, not able to hear, still it is okay, we can make out. But if the delay is there, then the real-time communication can affect. Delay is beyond a certain threshold. And for some applications, the throughput is more crucial. So like file transfer application, right? So file transfer applications, there we just check that, okay, in a given amount of time, how many bytes, how much time it took to transfer or download a file of 1 GB file. So based on that, we analyze the performance of the application. Okay, this file transfer application is a better as compared to other application. So we just look at that. Okay, if I transfer 10 files, I transfer out of these 10 file of 1 GB file, and average it took let us say 10 seconds or 15 seconds kind of thing. So that means that's a good. Uh, it is dependent on, I say this, so application is using some underlying protocols, and then the various delays which are not in control of the application. But yeah, some optimization can be done at application level, the protocol which is chosen. So largely for the delays, applications are dependent on the network only, means different hops, how many hops are there, then at each hop means how much the packet is delayed. The queuing delay which can vary at each hop. That depends upon the how much my network is congested. Now this throughput is measured in two ways, or that one way is the instantaneous throughput. You might have observed if you are using some peer-to-peer application, means BitTorrent and also downloading some files or application, some data. So this BitTorrent application, they shows instantaneous throughput during the downloads. Means every 2-3 seconds they show that, okay, this is the rate currently at which you are downloading, this is the rate currently at which you are uploading. So it shows uploading, downloading, both rate it shows. So that is instantaneous bandwidth, means at a given point in time, what is the rate at which the data is transferred. Then another way of calculating the throughput is we calculate over a period of time, let us say average throughput. Okay, so that gives me that, okay, usually for file transfer means we use the average throughput. Instantaneous throughput doesn't matter. Instantaneous can be it very high and then maybe go down low, and then overall downloading a file, how much time it took, that is more relevant or more important for the file transfer application, right? So now another thing, how much throughput we'll get between the 2 points, how it is. So for that, we'll take one example. Suppose I have here one server is there. Okay, so this is server, and this server is connected to one router, right? I say this is a R is a router, and this the link between the router and this server, the link bandwidth have the RS. Okay, and there is another link between. So here I have a one client. Okay, So let me do this thing. Yes. So this is a client machine is there, right? So this client machine, the bandwidth between the router and this client machine is, let us say, RC. Now, suppose this client is requesting something and then the server is pushing some data in the network. So the server is sending that data. So I'm saying that the data flow is in this direction. Data flow is in this direction, right? And now I want to know that how much throughput is there. So what throughput I will receive in this case? It's a two hop, you can say, network. So between the source and the destination, there are two links are there, right? So the throughput which is received or between by the client means at what rate the client will receive the data from the server. So it will depend in two conditions. Say for example, if RS, the bandwidth, this is a bandwidth, so it is bits per second, BPS. It can be kbps, mbps, gbps. Right now this is not our concern. So here also this is a bps. So if RS is less than RC, means this bandwidth is less than the this link bandwidth, then what will happen? Whatever the data which is sent over this link, that data will be uh, so here on this router, will there be a queue? No. At this router there will be no queue, because on this side it is receiving. So this side it is receiving at a lesser, you can say, speed, because RS bandwidth is less as compared to RC. So whatever it data is sent over this link, it will be quickly transmitted over this, because this link have a more bandwidth as compared to this link. So in this case, the throughput will be constrained to, what will be the throughput in this case? Throughput will be RS. It is constrained by RS. So whatever he says, RS is, suppose is a 10 Mbps. So if in this case I can take specific example. So this is a 10 Mbps. Let us say this is a 20 Mbps, right? So I will get a 10 Mbps. So my throughput will be equal to RS, and that is 10 Mbps only in this case. If it is like this, if RS or RC is RC is less than RS, then what happen? From RS, the data is coming on this link. The data is coming, incoming data rate is high as compared to this router can transmit the data on the RC link. So here a queue will be built up, right? Because that speed gap, the bandwidth gap will increase the here this buffer will be occupied, and because real networks buffers are finite size, so this buffer will be becomes full at some time, and then even in a worst case, if the speed is RS, the server is sending at a higher rate, then the router can push the data on the RC link at the, so then the packet at one point of time, packet will start dropping also, packet loss also will start. But in this case, my maximum throughput will be constrained by RC. So in this case, the throughput, so throughput will be R equal to RC. So you can take some example. Again, now I'm taking, let us say this is a 10 Mbps and this is a 20 Mbps. So you say that per second 10 MB, 10 MB, 10 megabit of data, you can say balance will be there, and that 10 MB, 10 MB will increasing every second. If the continuously this is speed the server is sending, then ultimately at some point of time the packets will be start dropping. But my throughput will be constrained with the RC in this case, that is 10 Mbps. So in this case, I will say this is RS is my bottleneck link. This is called as a bottleneck link. So between source and destination, a link which having the minimum bandwidth, that link will become a bottleneck link. So in this case, my bottleneck link will be what? RC. So my RC will be bottleneck link. Right. So like that, if so say it is applicable to multi hop network. Uh, so between source and client, let us say, or source and destination, if it is multiple hops are there. So one of the link which have the lowest bandwidth, that link will become the bottleneck link, and the throughput between the source and destination will be constrained by this bottleneck link. Okay, so this is very important concept that you should understand. Okay, so now I think this is over about our the preliminary part. Now we are moving to the internet structure. A little bit I have already talked about in the very first lecture that okay, what is network and what is internet. Here we are going to basically the formal, you can say, definition of internet. Means there we in abstractly we did okay, multiple networks interconnected. Now what are these multiple networks? So these multiple networks are, you can say, so basically when you take a connection either in organization or at home, you need to contact to the service provider like BSNL, Reliance, Tata. So in our country, these are the service providers, and every country have like that the service providers. So these service providers have an access network, and through the access networks, we clients connect. Now client can connect their network, means they have a local area network that can connect, and you can have a maybe just one home connections are basically one device we connect, and through that we using the wireless access point we can access the multiple internet we can access over the multiple devices, right? So like through the access network you connect. Now the question is how these access networks is to be connected. So these access network, because if these access networks are not connected, then suppose this end host A, how it will send the data to this end host if there is no connection is there, right? So for that purpose, one way is that okay, we can interconnect like this. So that is not scalable. Okay, as the number of access networks are increasing, and they are in thousands and millions of access networks are there, right? So that's not going to be work. So we need some kind of a global ISP. Okay, we call it a internet ISP, stand for the internet service provider. So a global ISP there, that's a means infrastructure, huge infrastructure that interconnects all these access networks across the globe. But this again, this global ISP is not going to be scalable because single global ISP will not scale. Nobody will able to maintain across the different geographical area across the countries. So there is a concept of multiple ISPs are there, multiple global ISPs are there. So we have ISPs. ISPs are categorized like a tier 1 ISP, tier 2 ISP, or tier 1 ISPs. Tier 1 ISPs have the large reachability as compared to the other tier 2 and tier 3. So they have maybe multi-country reachability or in a large geographical area. Right? So they are categorized like tier 1, tier 2 ISP and so on. Then you have like these are basically access. There also ISPs are there. They call as a local ISP. Then the regional ISP concept is there. So these all these this categorization is based on the amount of, or you can say the geographical area covered by these ISPs, means the area in which they provide the service, right? Some of the ISPs are their services are limited to one state only. Let's say, for example, in Rajasthan, in India, maybe some ISPs they work across the multiple states, and some ISPs works across the country, right? So like that, the different levels are there. So now these ISPs, let us say these multiple ISPs are there, and each ISP provide the connectivity to their customers. Means they further uh, give the service to the local ISPs, and the local ISPs through the local ISPs the customers connect to the internet, or they take the services from them. So now these multiple ISPs needs to interconnect, right? Then only the complete end-to-end connectivity will be achieved. So there are two ways to interconnect these multiple ISPs. One is this way, it is shown in the slide. So we call this as a peering link. Means ISP is one of the router of this ISP and one of the router of this ISP. It is interconnected, right? So this router and this router. So that's a peering points. Like here also, this router of ISP A is connected to this router. At least one is required. Even that is not a restriction. It can be. It can also possible that okay, there are two routers of ISP A are connected to two routers of ISP C. Means they have a multiple connectivity. That is also possible. Means that there's technically there is no issue in that. So this is the one way of peering, means direct one-to-one connectivity. Other way is that okay, there are kind of a exchange points are there. So like you have in a telephone exchange where multiple networks interconnect at one exchange of you can say office is there. So similarly for internet also there are exchange points are there where multiple ISPs they connect, and these exchange points are administrated by the different third-party organizations. So they maintain all internet connectivity, all the connectivity issues or any failure on any you can say cable cut and all these issues, power related and all. So that's not a burden of these ISPs. So sometime if so that multiple, so some of other ISPs they connect. So here on this exchange point, multiple ISPs can interconnect here. So these are exchange points. So these are the different ways. You can see here this exchange point ISP A is also connected, ISP B is also connected, ISP C is also connected. So the traffic will be on this exchange, from this exchange point A to B, A to C, and vice versa. The traffic can be routed from here. Then, as I said, that okay, there may be a regional networks or regional ISP concept is also there. So that also needs to be connected. At least one or two upper level ISPs like country level or that global level ISPs to get the complete connectivity. Because it should not happen that okay, some of the users they are not able, you are not able to access some of the services on the internet. That kind of service you will not take it definitely, right? Because as when you are getting the internet connection means you want to, there should be no restriction in terms what you can access or you cannot means connect to some particular servers or services. Then there is another concept which came in last few years, that is that the like Google, Microsoft, and Akamai. These are all content distribution players. Means they have huge amount of contents, multimedia or any sort of content, and like Google have now acquired YouTube. The Microsoft have their own content. So what they do, whatever content they have, they provide the content distribution service. Means people can upload their content there and then the millions of people can access. So we call these as CDNs, content distribution networks, right? So these players also have their own you can say infrastructure, and they deploy this infrastructure for such that so that people can access their content from the nearest point, right? So when you are accessing, let's say from the YouTube, so it's not like the YouTube have a multiple replication replicated server across the globe. So when from India we are accessing, maybe it is connected to some server in Hyderabad or maybe then Singapore or something, and somebody is connecting from Europe, then maybe some European country that server is accessible. So content distribution networks ensures that the users are getting the content from the nearest possible location, nearest geographical location to that point. So uh, so that the latency can be controlled. Otherwise, if everybody is connecting from the US server only, then you know that there will huge latency will be there. Also, that one server or one physical location will become the single point of a performance bottleneck as well. So that's why the replication is for the scalable, to make it scalable, the sufficient replication is required. But the challenge in the replication is what? The content consistency. Okay, so they have different mechanisms for means the consistent for the content consistency across all servers. Okay, mostly static data is shared. So static data there is no issue, but yeah, some dynamic data is there. Then there is a issue that if it is updated, then the updated copy of the data should be accessed by all locations. So you need to means across all replicas that content needs to be replaced. So till this point, do you have any question? I think we have 25 minutes I have continuously speaking, so maybe you may have some questions. Any quick question, if anyone's mind? Yes. So if no question, then can we move to the next? Please feel free to ask question, right? So although it is online, but yeah, still as far as possible, we'll try to make it more interactive, right? Okay, so in that case, I'm moving to the next. So now we are moving towards that. So I want to just show in this slide that I have pointed out in first lecture that DARPA was the project for the internet architecture, which was in 1980 sometime. So there was some design goals are there. So these are the design goals for that time. Means the team has decided that for the internet architecture. So one was that connecting the existing networks. That time there were a network which is called as ARPANET and ARPA radio packet radio network, and few more such networks were there. So their first aim was to connecting the existing networks. Then the second goal was survivability, means in any circumstance, any failure, because there are multiple devices are there, any device can fail, right? So in case of failure, any intermediate device fails, then the endpoint should not suffer due to that. Or any intermediate device, let us say restart or maybe power failure, any kind of means failure occurs, that should not affect the end-to-end communication. So you see that do you need to bother about that? Okay, between suppose when you are accessing internet, maybe between you and that the service which you are accessing, between that there may be a multiple hops are there. Now these multiple hops, maybe out of these hops, maybe anybody can any device can be restarted or something can happen. So there is you don't have a control over that, right? And this is happening actually, right? So but still it's a very rare that okay we are trying to connect someone or we are using some application and in between something has happened. It can happen that okay at my side some network failure is there, so that I need to take care, but intermediate failures are not affecting the end-to-end communication. That kind of a robust you can say survivability have been achieved. Okay, so I'm not going to go in much detail of how this survivability have been achieved. You just think of that, okay, how this survivability might have been achieved actually. That when that any two endpoints are communicating and means intermediate routers, definitely they are failing, everything is happening, some restarted somebody, because they are not in your control, somebody else is controlling, right? They may restart their routers and all, but it's very rare that okay we are getting means our communication is stopped, provided that okay both ends the network availability is there, both ends means the ends which are communicating. Huh. Uh, it may be sometime it is possible that okay your internet connect at your end there is no problem, but internet connectivity is lost. That happens when sometime when the fiber cut happens, okay, because and that is the situation is something like that, that suppose this is the internet and you are somewhere here, that is you are and somebody is that's another person is, so there is a communication between A and B. Now between A and B, the failure occur in such a way that okay it is dividing the entire network into two halves. So one one remote party is on one side of the network, other is on other side of network. This is the only situation, means that then we call it the network is fragmented basically. So in that case, definitely you will not be able to communicate. But except that, any other failure is going to be covered, and you will be maybe there may be some disruption, but immediately there will be alternate route will be selected, and then you will be able to start communication, and your connection will be reestablished. And this is achieved. because there is a lot of redundancies there in the network, core network. And there is a principle which is used, which is called as a fate sharing principle. Okay, I'm not going to discuss this principle. You just explore what is fate sharing principle in the internet, and maybe you can put this on discussion forum, those if you uh, get more interested into that. Okay, then support of the multiple types of services. Different services you should support, they should be differ in the speed, latency, and reliability. Next goal was to must accommodate a variety of networks. So this third and zeroth goal, basically more or less they are same. So connecting network means existing networks were a different variety in the sense they are uh, working on the different technologies like Wi-Fi. Now in today's context, I'm talking about Wi-Fi. You have Ethernet, satellite network. That time means also some different kinds of networks were there. Packet radio networks are there and all. So these networks are working on a different technologies. Technology in the sense that the links, the speed of the link, and what kind of links are there, is a wired, then what different wires are there, then speed at which the network work, kind of a devices which is connected, and there's so many different kind of things are there. Then it should allow distributed management. Certainly you cannot go for the centralized management for this kind of a huge system. And the host attachment should be have a low level of efforts. With the low level of efforts, we can attach the host and host, and it should be cost effective. Any solution which you want means that it should be cost effective, and then allows the resource accountability, means how much resources have been used. That so you might have observed that, okay, as I'm writing these or typing these goals from 0 to 7, then the font size is reduced. Okay, so it is not accidentally, it is intensely. So you see that, okay, actually up to the goal number 3 is successfully means that have been given more emphasis. Goal number 4, 5, 6, 7 have been, these are, we are not achieving, means these are not, these goals have been not been perfectly achieved in the internet architecture. Distributed management is there, but the distributed management means we don't have any application on the internet. So we don't have any test bed kind of thing or any simulator or any infrastructure. Through that, we can run that application, and then we can get the information about the resources, how much resources are left, or means that kind of a centralized, that kind of a information gathering from the various nodes in the network, so that kind of application is not there. So this, on that front, the internet is lacking, and the other aspects anyway. But the primary goal was that existing, connecting the different networks and different types of network, and that is have been successfully achieved. Survivability is also achieved successfully. Okay, so now this, you know that, okay, this there are different, you can say, uh, kind of a functionalities are, means what are the basic functionalities, means uh, node, when node A is communicating with the node B, so you need to establish a route between, then at each hop that packet, the messages which are sent by A to B and needs to be forwarded, right? Then some kind of a congestion control, some reliability needs to be achieved, right? And these nodes have maybe have a different addressing scheme they are using, right? So there are variety. Internet is not a simple system. It's a complex system. A lot of functionalities are there. Diverse applications, different kind of applications, right? Different kind of hardwares are there. Multiple devices have been used, and you know that over all these means users should be able to run the applications. So it's a complex system. And you know that the largest distributed system on the, means on earth is what? Internet is the largest distributed system. Any other, because it's an example of, typical example of a distributed system, and this is the largest application, you can say, distributed system application, internet. Okay, so this complexity, how to deal with the complexity in a system. So if you even internet is a very complex system, but yeah, even a smaller projects also, how do you go for that? You go for a design, modular design. So break up that system into multiple, you can say, modules. So internet also was uh, broken up into the different modules, and these modules have a well-defined interfaces. And each module performs some specific functions. It's not a monolithic kind of a means code is written, or you can say, because that's very difficult to manage and you cannot maintain that. Means if any change, if you are doing in a monolithic code, even you say 10,000 line code is there and doing some functionality you are achieving, if any modification you have to do, then it's very difficult. You need to make it modularize different functions. Then with a modularized design, it is easy to change. Any function you can change without affecting the other functions. Only thing is you need to just intact the interfaces, correct? So each module performs specific functions. Implementation of a module can be changed within. So suppose one module is calculating, let us say factorial. Now factorial method implementation you can change any point of time. As far as and so that is not going to affect the rest of the system. You need to just intact the interfaces, that it is taking a number and then providing this function. This function is providing as a result as a factorial of that number. But algorithm of the factorial calculation you can change anytime, and your rest of the system will be intact and no change is required in the rest of the system. So that sort of thing is required. So we will see that, okay, how. So for that purpose, the reference model which was used, which is called as a OSI, Open System Interconnect, which is used in the to develop the internet stack. So 7 layers are there in that. You can see layer 1, 2, 3, 4, 5, 6, 7. Right. And so you have two types of you can say devices or the machines you can connect. One is at end host. End host you connect, like your laptops and a desktop machine and server machines and all. And then you have intermediate devices which are switching forwarding devices are there. So core of the network which you have, right? So there are two types of devices, means category wise. Although in end host also you have different kind of a mobile is end host, laptop is end host, but means technically all are same, right? So internet means so okay. So this at end host all 7 layers to be implemented as per the OSI reference model, right? All layers are implemented at end host, and the intermediate devices. Some of the intermediate devices they have implemented only up to the layer 3, and so this we call as a so the layer 3 devices we call as a routers. So now onwards we'll differentiate between the routers and the layer 2 devices, which is also called as a switch, okay, or layer 2 switch. More specifically, we say it's a layer 2 switch. So here in a core, we have two types of devices. One is the layer 2 switch device and a layer 3 switch device. Layer 3 switch device is called as a router. Router works at to connect the two networks, two different networks. And switch connects the one, say for in a local area network, you require just switch. Okay. So you have one local area network, you have multiple switches are there, and through that you can connect your end ports. And suppose one local area network is there in BITS Pilani, one local area network is there in the IIT Delhi. Now these two needs to be connected, so they need to connect through the router. So that's the difference. Now, as I said that, okay, in the internet stack don't have the all 7 layers actually. Internet stack have a 5 layer. So that's why it is called as a TCP IP architecture. So TCP IP architecture have the 5 layers. The reference model is used. This is means OSI only, but the TCP IP have 5 layers. So which 5 layers are there? First we'll look at. Or which 2 layers are missing in the TCP IP? These 2 layers, presentation layer and session layer, are not there in that. So presentation layer, session layer functionality is either implemented in the application or transport or in the collaboration in both of them, right? So can be session layer functionality is push into the transport layer, presentation layer functionality is push into the application layer. And then the rest of the layers are there. I mean, transport layer is there, network layer is there, data link layer is there, and physical is there. So 4, and then the application layer is there. So you can say with these 3, only 1 layer is there, and then remaining 4 layers are there. Okay. So now in this layered model, so what is the, you can say, beauty of this layered model is, so a layer can implement multiple protocols. Say for example, transport layer. Okay, transport layer, there are 2 protocols are there, TCP and UDP. You can implement multiple protocols also, right? Similarly, at the routing layer also, we have a multiple protocols are there. RIP is there, OSPF is there. Network layer also, we have a some of the networks they implement RIP, some of the networks they implement OSPF. Okay, so or new protocols can be added, and that is not affecting my rest of the remaining layers. And each layer relies on services from layer below and export the services to layer above. Say for example, transport layer. So if I say these 2, presentation and session, is not there in TCP/IP. So with respect to the TCP/IP talk, then the transport layer export its services to the application layer, and it uses the services from the network layer, right? So this way the layer, so, and that is through the well-defined interfaces are there. Okay, so this way this layered model work. That's the fully layered model means any, and that is applicable to this definition is applicable to any software development which is a layered model, right? You know, there's one of the technique of in the software development in a software engineering which is defined as a layered model. Okay, you have layered model. Modularize in the different layers. The functionality of a complex system you have divided into multiple layers, and layers can change without the disturbing the other layers, because as far as the interfaces are well defined, then within that, today I am doing the routing with one protocol, then tomorrow I change that routing protocol with some. So as far as the services which is this network layer is exporting to its next layer, that services are intact, then the internal implementation doesn't matter. So this is the functionality of that's based on the TCP/IP stack, internet stack, which is a TCP/IP layer called TCP/IP model. So physical layer means delivers the bits between the 2 endpoints of a link, and these are the different mediums which you use to transmit the bits. Then data link layer delivers the packet between 2 end hosts in a local area network. So different examples of the data link layer: Ethernet, which it is there in our campus also. Ethernet called as 802.3 is the IEEE 802.3 is the number for the Ethernet protocol. Then Wi-Fi, which is 802.11. Then cellular, 2G, 3G, 4G. These are all layer 2 technologies. And the devices which is used at a layer 2 are called as a bridge or switch. Bridge is a slightly different from the switch. Okay, so that we'll see when we'll talk about these devices in more detail. So both are there. Bridge also can be used, switch, but nowadays all the bridges have been replaced by the switches only. The network layer that connects the multiple networks. Okay, then basically your internet is nothing but it's a network layer only. And if you look at so you have a different networks are there, and this internet is basically working as an overlay. So this internet is nothing but it is an overlay over these various networks. So it's a first you can say overlay network which was created is the internet only. Okay, so it just connect all these different networks. So it connect like an overlay only. See, overlay is created, and that overlay is called in internet, and the layer which is called as IP layer or network layer, right? And then the transport layer ensures the process to process data transfer. So the functionality wise data link layer and the transport layer are more or less same. When we'll do individual layer functionalities in detail discuss, You will see data link layer ensure node to hop by hop communication, right? So between two hops, maybe you need to implement the flow control, means node A should not send more than what the node B can receive at this moment. It should not overwhelm. So this is called as a flow control. So means reliability, A to all the packets which have been sent by A are reached to the B or not. So these things needs to be these are the basic functionalities can be implemented at the layer 2. Similarly, transport layer also. Transport layer is between source and the destination, and between source and destination there may be multiple hops are there, right? So this is 1, 2, second, third, fourth, fifth, and sixth. So it works at a two endpoints. Okay. Then finally the application layer, you know that okay, the different applications like mail applications, web browsing application, file transfer application. So that work again at a end-to-end point only, end-to-end basis only. Okay, so this is the way one way we can visualize the internet architecture. It's an hourglass architecture. So you see that hourglass architecture means you on top you have a variety of applications, so many different types of application, and bottom you have different kinds of network technologies, Ethernet, different protocols means different physical media, different medium access protocols, and then different like Ethernet, Wi-Fi, satellite, different kind of networks are there, right? So it supports so many different kinds of networks. So different kind of applications, they can communicate over the different types of networks, which are different in various aspects. And who facilitates this communication? This communication is facilitated by the IP. And this IP is a narrow waist. Narrow waist means minimal functionality it provides. Minimal functionality it provides. So what is a minimal functionality? Minimal functionality is best effort service. So no guarantee means it says a try my best kind of thing. So there is no guarantee. That's why internet is not reliable. As an architecture level, it is not reliable. All the reliability which we achieve in today's time that we achieve through the applications actually. But infrastructure is IP layer doesn't give the guarantee that okay, packet is sent by the node will be definitely received by the other node. No, at the other side of the node. It may drop, it may be delayed, and how much time it will take, that also no guarantee is there. So the IP layer cannot provide any guarantee, right? So that's why it is called as a minimal, it provides a minimal functionality, just transporting the packets which are coming from one node, which can be sent to the, which can be forwarded in such a way that it can reach to the destination, but guarantee is not there. So trade-off is there is no assumptions, the underlying network that okay, oh, this kind of link should be there on, and the packet size which is coming from the below network that should be of this size or that size. No assumption is there. What you need to connect something to internet, you need an IP address, that's all. If that machine or that device can be given an IP address, okay, that is fair, good enough to connect to the internet, and then you are part of the network, right? So that's why no assumption is there. But if the no assumption is there, the no guarantee is also there, that whether your packet will be delivered in time, no such guarantees there. So that's why it's called as a best effort service. Now question here is why this kind of architecture or this best effort service architecture was chosen. Best effort service architecture was chosen. So this is a question. Uh, uh, I say that indirectly I already answered, but okay, you need maybe you just think of it, that why this kind of architecture, why the reliability has not been, why the security has not been considered, why the reliability has not been considered as a part of architecture, not the part of applications, right? So that you think of it, okay? Maybe sometime if you have some answer, then uh, uh, I will tell you the exact answer. Okay, so finally we'll just look at this and then we'll rest our lecture. So now this, to understand this layered concept, so you see that, as I said, that the TCP/IP is a 5-layer model. So this at end host, application layer, transport layer, network layer, link layer, and physical layer, right? And within the local area network, you have a layer 2 devices, so they implement only link or physical. Then across the network means different networks are connected through the routers, and routers implement 3 layers. And this network layer is nothing but it's IP layer. So now you see that this animation is nice to understand. So application create a message. We call this as a message, and the same terminology we'll use throughout the course. That whenever we'll talk at application level, we call as a message, a chunk of you can say bytes, we call as a message. This message include the data plus the application layer header also. Now this application take help from the transport layer and says that, okay, please this message you this message you send to the destination, this destination in this case, right? So then it gives this message to the transport layer. Now transport layer will attach its header, means some control information, and that control information is helping to the receiving side. Just a moment. That control information is helping to the receiving side to deliver the message to the application layer. So you can say some information is written here. We'll see when we'll do the layer by layer our topics. Then we'll see what header fields are required here, which are included by the sender side, so that the receiver side using that can identify these packets and deliver to the application. Okay, so this header field is attached, and now at this transport layer we call as a segment. Now transport layer then hand over this you can say segment to the network layer. Say that, okay, now you forward it to the next hop, right? So it receives message plus the you can say header field attached by the transport layer header, and combined we call as a payload received at the network layer. So network layer add its own header field, because network layer requires some control information so that the packet can be moved from one hop to another hop, right? From one network to another network. So this is in this case, this is a one network up to this switch. This is a one network at a layer 3 level, and this is another network, right? So my destination is connected to another network. This destination host and host is there, that is connected to this router. This is a different network, and this is a different network. So at network layer, we call this as a datagram. So application layer, what we call message. Transport layer, what we call segment. And at a network layer, we call data. So whenever I say it's a datagram, this datagram is moving to this datagram, something means I am talking at a network layer. Okay, so that's a, you can say, nomenclature which we are going to use, and same nomenclature is used across the any textbook which is of the networking. Then network layer will then give this packet to the link layer. Means, okay, so finally, because the link layer is where that, okay, on the physical wire that packet will move, wire or wireless, what is there. So link layer also will attach its own header field. So HL is added, and then here we call this bunch of bytes, this we call as a frame. So anything other than the HL here is called as a payload. This is a payload at the link layer. And now on the physical wire or physical medium, if it is a wired connection or wired network, then this frame will move bit by bit over the link. So it is moving now, and it reached to the, so till this point it's next hop it will reach, because for this network this router is a next hop. Now here the packet will be delivered to the network layer will give to the link layer. Link layer will give to the network layer, right? And then here you can see, so the network layer on the receiving side, you say the network layer will give to the link layer on this the receiver side network, and then the from the physical link which is connected to this network, it is reached to the destination. Now destination, the reverse process will start. Okay, so means physical layer will hand over to the link layer, and then the link layer will remove, it will use this link layer header and the process the packet and then hand over to the network layer. Now network layer will process the packet based on its header and then give to the transport layer. And the transport layer will process the packet based on the information in the HT, that is a transport layer header, and then give to the application and the application. So the message which was created here by the source, this M message, now it is delivered to the application layer. So this is a complete journey from a source to the destination, or a source application process which is running at a source side, and that process is communicating to the destination side application. So this way they can communicate. Okay, so this thing terminology we can can understand with the help of this example, which is analogy, which is organization of air travel. You know, in air travel, that there again is a complex system, means multiple functionalities are there. So first, if we want to travel, then first you need to purchase the ticket from the agent. Okay, so now purchasing ticket is a module. So I can purchase from agent, I can purchase from the counter, or different methods, and over the period of time, maybe different mechanisms of the ticket purchasing can be evolved, like online purchasing and through agent or something like that. So once I have a ticket, valid ticket, then okay, I can go to the airport, and then I do the baggage checking first, right? So I should have a boarding pass. So using that only I can do that, and then uh, then the next phase is the gate loading. Now gate loading also, it can be a manual process or it can be automated. That also can be changed without affecting the rest of the system, right? And then the plane go to runway, okay, for takeoff, then plane routing. So now the plane routing is a completely different system. At any point of time, it can be changed without affecting the rest of the operations of this system. So then plane goes from one hop to, means the route which is decided by the air traffic control, and then it destination it reach, then it land, then I unload myself from the gates, then I claim the baggage, and then if I have any feedback about this my travel, then that I can give to the, there some counter is there, which means, and that's, so you see there's all these different uh, we can say functions are there which are implemented at in a modular fashion. So it is analogous to your internet application, right? Okay, so each layer have its own functionality like that in internet also. So this completes our first chapter of the book, and now formally we will start the first layer in the next lecture onwards, that is our application layer.